Hey pre-calc, I got a new video for you. It's section 2.4, lesson 2. I wanted to kind of piggyback off the concept of vertex form from parabolas, quadratic equations, to inform us sort of like, okay, what happens when this similar looking vertex form encounters cubed functions, functions to the fourth power, functions to the fifth power, and just see if we can kind of glean some, I don't know, some patterns so that we can really extend that concept well beyond parabolas. So I'm going to do an example from, different parts of the homework, and then that'll sort of act as our notes. So make sure you put those down. I'll still check them as if it were a homework assignment. So let's do this. So keep in mind, y equals a times x minus h squared plus k gave us the vertex of any parabola. My question is, what is my question? My question is, what does it look like if I change the square to a cubed? Yeah, that was my question. Well, it's not going to look like a parabola, right? However, the idea that the k value for a parabola is a vertical shift is going to mean the same thing for a cubed function. So this right here, x cubed minus 2, means you would shift 2 units down whatever x cubed looked like. Well, if you remember, x cubed follows the pattern something very similar to this. So you can think of it as, oh, it shifted down 2. And then usually 1, 1 and -1, -1 are kind of like touchstone pieces for how to graph the thing. It's 1 away from our center. So I guess at this point, if you wanted to just plot points, that's probably the easiest way to talk about this. So 0 cubed, you get -2. 1 cubed minus 2 would be 1 minus 2. You'd get -1. -1 cubed is -1, minus 2 is -3. So left 1, down 3. Now, what I'm asking you guys to do is, instead of finding a bunch of different points, please just flesh out the curve after you get sort of the centerpiece here. Because once we start plugging in things like 2 cubed is already 8. 8 minus 2 is 6. So we can plot it on this teeny tiny grid, but you go -2 and we're talking -8, which minus 2 is -10. So keep in mind that that's what the curve looks like. It's almost like a half parabola that shoots up way quicker than a parabola, and then basically loops around and does the exact same thing going towards the bottom. So there's our function. I think you can extrapolate what's going to happen with this h inside here, right? Oh, horizontal shift. What happens in front there? It's going to compress it if it's a fraction. It's going to flip it. It's going to reflect it if there's a negative. Okay? So same concepts with parabolas. Just a totally different curve. Let's look at number 6. So we talked about cubed functions. What about functions to the fifth power? Well, like I was just saying, the plus 1 in there means that we're going to shift our center. It's sort of like our center point, not like the center of a circle, but just the central location by which we kind of like see changes in the function. This has a -1, -3, not vertex, but central location. Left 1, down 3 is going to be an interesting point there. So now if we plugged in just some numbers like, I don't know, plug in 0. 0 plus 1, 1. 1 to the 5th power, 1. 1 times a half, half. Minus 3, -2.5. Okay. So my question to you is, cubed functions had kind of this symmetry going on where it looked like a parabola that shot up really quick. My question is, does this have similar characteristics? If the point is -3.5 when you move 1 in this direction, then it does have similar characteristics. So let's try it out. Plug in -1, 2. -2 plus 1, -1. -1 to the 5th power, still -1. Times a half, -half. -half minus 3, -3.5. It has the identical properties that a cubed function has if it's put in this form right here. So if you want to, you can flesh out the rest by plugging in 1, 1 plus 1, 2, 2 to the 5th power, 32. That's big. And then times a half is 16. 16 minus 3 is 13. We're still almost double off the grid. So what it shows here is that the curves are way more pronounced. They're sharper and shoot up quicker. So this is what you're looking at. And then it's going to do kind of the same thing in the opposite direction. So then every odd power that shares this type of, what would you call this? Just standard form, all right? It's not a vertex form, but it looks very similar to vertex form. They kind of share that exact same pattern so that you could predict what x to the 7th power looks like. It's going to be almost like that. They're almost like sharp turns. Okay? So odd powers have a very, odd powers are kind of like on the same team now. They show the same curve pattern. At least the ones that look like this. Let's look at number 9 now. What happens when we kind of go back to evens? Like, what's the deal with ax minus h to the 4th power plus k? Same stuff. Shifted right 1, up 4. And the question is it going to be some kind of centerpiece? You know, if you have a calculator with a table, it's not a bad idea just to bring that out and use the table. So I have one of those. So I'd go to, it might be the table, it might say y equals. We'd plug in -1/2 times the quantity, parentheses, x minus 1, close quantity, to the 4th power, plus 4. Yeah, so if I go to my table, 1 corresponds with 4, 2 corresponds with 3.5, and 0 corresponds with 3.5. Ooh, interesting. If we go to 2, we already did. Let's go to 3. 3 is -4. 1, 2, 3. 1, 2, 3, 4. Oh boy. And, -1 is also -4. We've got symmetry. Woohoo! It looks just like a parabola, flipped upside down. Except it's way sharper. All right, so, I didn't really do x to the fourth power justice with that, but I hope you guys can see that the half is supposed to make a parabola wider, okay? It's supposed to compress it. This is the compressed version of an x to the fourth power. An x to the fourth power is way more stretched, so to speak. It looks like a super stretched parabola. So then hopefully from there you guys are looking at this and you're like, okay, I can predict now what x to the 6th power, to the 8th power, to the 10th power, to the 100th power, to any even power, if it has kind of like this format, what that's going to look like. So, number 11. It's going to look like a super sharp parabola. Opening upward because it's a positive, shifted down 4. So go down 1, 2, 3, 4. I mean, I can go to my calculator and see what the values are at, 1 and 2 and a bunch of other ones. It ends up being 1, -3, -1, -3. But 2 goes all the way up to 60. Right, so hopefully this makes sense. Patterns? Yes. All right, and going along with graphing functions, polynomials is really what they are with degree greater than 2. There's another thing I wanted to talk about that's actually not too big of a stretch for you guys to figure out. I'm talking about creating functions that are given certain characteristics about their zero and their degree. So, the degree of any polynomial is its leading power, okay? So, say you've got y equals 50x to the 12th power plus 7x. The degree of this polynomial is 12 because the leading power has an exponent of 12. So when they tell you you got a degree of 2, that means x squared is your leading power. Degree of 3, x cubed is your leading power. Degree of 50, x to the 50 is your leading power. So let's just pick one of these. Number 16. Sorry, I'm trying to manipulate the wrong computer here. So 16. I'm creating a polynomial, so I'm just going to call these functions f of x. You could call them y if you wanted to. I'll call them f of x. This equals the place that has x equals -2, x equals 4, and x equals 7 as zeros. So if your x equals -2, x equals 4, and x equals 7, if these are your zeros, that means you can work one step backwards to compute what that function would be. Here's what I mean. When you solve an equation, you get x by itself, right? What if we brought the constants back on the same side as x? That means that one of my factors is x plus 2 when you set it equal to 0. One of my factors is x minus 4. Sorry, that's a weird looking x. Yeah. And then the last factor is x minus 7 equals 0. So we need a polynomial with degree 3. And these 3 zeros, if I were to expand that out, I'm not going to right now, I've got it. Does that make sense? Because it's going to eventually be x times x times x when you expand the whole thing, and that's x cubed. So we satisfied both the degree and the zeros. We've got a polynomial function. Now, technically, I'd have to expand it to call it a polynomial function. I'll decide in class whether I want you guys to expand them, okay? Nah, don't expand them. Okay, sorry. Let me give you guys number 19, and I think that'll do. So I've got x equals -5, 1, and 2. Hopefully you saw the pattern of, oh, it's just the opposite of whatever the 0 is. So -5, that's x plus 5. Positive 1, that's x minus 1. Positive 2, that's x minus 2. Should be that simple, right? It says degree 4. How do you create 4 degrees if I'm multiplying x times x times x and I'm only getting x cubed? Well, usually here's what students respond with. Throw an x on the outside. Now, true, that creates a degree 4, but it also creates another 0. X equals 0. Which is not one of the zeros listed. So I can't just put an x out there. So what am I supposed to do? Well, I could create a double root, which basically just means, what if I were to repeat one of these factors? I wouldn't be creating a new 0. I would just be creating a more inflated polynomial with a bigger degree. So let's say we multiply this whole thing times x minus 2. Okay? What are my zeros? Well, it's still just -5, positive 1, and positive 2. Because positive 2, one of the zeros is positive 2. What's my degree? If expanded, this thing's going to be x times x times x times x. It's going to be x to the 4th power, which is degree 4. So we made it happen. Yeah. Now, a shorthand version of this is basically just saying, are we short a degree? We're short by 1. All right. Double that. We're good now. All right, that's all I got. Hopefully this was helpful. You guys enjoyed it. And I'm so thankful for you guys watching this stuff. That's all.